Hello everybody. Today we will be just talking about how the different equilibrium processes can control the complex formation. As we have seen that whenever we have a metal ion and is forming some complex with the ligands, and if we just simply consider that there are 4 such metal ligand bonds which are present in the final product, that means the final complex. So, this number is very important, that means the 4 metal ligand bonds are forming, and if we just think that Mn plus was there, which is forming first one metal ligand bond, and if this particular process is reversible in nature, that means all these together, that means formation of one coordinate bond, these we all the time we are considering it as a coordinate bond, such that if we have copper 2 plus, the bivalent copper ion is present in the solution, which is dissolved in water. In that case also we have the copper OH2 bond, and this particular thing is there and they are in equilibrium. So, we see that the metal ion, the ligand and the complex, all these are present in solution. So, if they are in equilibrium and depending on the reaction condition and depending on the medium, how we know that what percentage of the reaction is going from left to right, that means the corresponding affinity of the metal ion to react with the ligand to keep the corresponding complex species, at least one metal ligand bond is forming over there. So, that equilibrium process, how we can monitor, that is the question, that we know the corresponding concentration of the metal ion. So, the monitoring of the concentrations of the ligand and the concentrations of the complex species. So, if we can monitor all these species by some mechanism, so monitoring of these concentrations, so we can get some idea that how much metal complex is forming by reacting the metal ion with the ligand to give us the corresponding complex species. So, during the complex formation, we can have that all these species starting from the complex, the metal ion and the ligand, they are all in equilibrium. So, in today's class, we will just consider how the equilibrium processes are taking place and how the different species can contribute for the equilibrium process, because this is a very important thing what we just can monitor in the solution stage. So, in solution, the complex which is giving us some equilibrium process and how we can monitor the corresponding equilibrium process, such that we can evaluate some constant related to this particular complex formation. That means, the equilibrium constant which can tell us that how quickly the corresponding metal complex will be forming from the individual components. So, that particular equilibrium constant for the forward reaction we can measure, and the constant can be monitored for the different stages of the equilibrium. So, we will be talking in this particular class about the coordination equilibria. So, we have more than one such equilibrium processes. If we just consider that there are 4 ligands and one after another the ligands are coming and bound to the metal center. So, in that particular case, how we can talk about the stability of the corresponding complexes, how much stable the complex is. That means, if we get this particular Ml4 species from the individual corresponding aquated or the solvated metal ion, and how much of these species are forming immediately when we give the corresponding stoichiometric amount of the L. That means, if we use M with 4L, whether we get the corresponding Ml4 species and how much this particular Ml4 species is stable, that we can also monitor. So, the stability of the complex can also be found out by monitoring this corresponding equilibrium process, because if we see that this Mn plus was there and we can have large number of bound water molecules. So, at different intermediate stages, we just remove the water molecule as we react it with 1L, remove the second water molecule as we push the second ligand, similarly the third and the fourth. So, these stages basically tells us that how quickly we can achieve the corresponding stable species, because the other species like that of where we can have ML1, ML2, ML3 etc. are not so stable. Only the ML4 species had some stability compared to the intermediate species. So, then we can find out the corresponding stability constant for that particular process. So, how we can find out the corresponding stability constant and determination of that particular stability constant for these complexes and give us some idea about the stability of the complex. So, in that way we can define a stability constant, which also we can consider as a formation constant, that how the metal complex is forming in the solution, as well as the binding constant, because the metal is binding the different number of ligands to it. So, we can consider it as the binding constant. So, when we are talking about the metal and the ligand system, we will be talking about the corresponding binding of the metal ion with that of the ligand. So, it therefore an equilibrium constant for the formation of the complex in solution. So, how quickly we get the corresponding complex species in the solution? If it is a 4 coordinate one, how quickly we can achieve the corresponding 4 coordinate complex, or if it is a 6 coordinate complex, then whether we are able to get the corresponding 6 coordinate compound from the 4 coordinate one, or some other mechanism can be operating over there such that we get the corresponding octahedral complex. So, situation is little bit different, as we have seen that we can go up to a coordination number of 16 say. So, if we want to have a corresponding compound where the coordination number of 12 at least can be achieved around the metal center. So, there will be definitely some 12 stages of formation of one after another metal ligand bonds. So, we have a pretty complex expression for the corresponding stability constant. So, how we get the corresponding stability constant? It also gives us some idea about the measurement of the strength of interaction between the reagent that come together to form the complex. So, when the reagents are metal and ligand, we will be talking about the corresponding formation of the metal complex. It can be some other non-covalent interaction, so or some supramolecular interactions at the same time. In that particular cases, we can have one component is binding to the other. In that case also the species what is forming on the right hand side due to the binding of the two fragments on the left, we call it as a complex species, and in all these cases we can have the corresponding constant, which constant is known as the corresponding stability constant or the formation constant for the complex species. So, it is true for some other physical system where we are not talking about the metal and the ligand, but some other biochemical reactions, some supramolecular interactions, some non-covalent interactions. In that particular case also the same types of expressions are useful to find out the corresponding equilibrium. So, first thing what we can see that we can have the interactions when we have the compounds which is forming from the metal ion and the ligands. So, in these cases we can have two kinds of complexes. When metal and the ligand is forming, it is one complex, and the supramolecular complexes such as host caste complexes and complexes of anions. So, when we have no such physical quantity like metal and ligand, but we can have a host such as some big inorganic cage or some organic cage. So, some cage molecule or some say crown ether, but in case of crown ether we know that it has some donor groups, oxygen based donor groups, which can coordinate to the metal center like sodium, potassium, lithium, etc. So, in that particular case we can consider it has a complex equilibria. So, complex formation can take place, but within the cage molecule when it is basically trapping. So, if it traps the guest from some hydrogen bonding interaction or some hydrophobic interaction or some van der Waals interaction. So, we get some interaction where the cage molecule, the same cage molecule can trap the guest. So, if we have this particular species, that means if we have the guest plus host which are not bound, and on the right hand side we have the guest which is bound to the host, then also we can have this particular situation that complex is forming. Similarly, we can have the anion binding. So, some species which can also be there where we can have some hydrogen bonding donors. So, if hydrogen bonding can play some important role for some anion, say Cl minus. So, hydrogen bonding can use for some NH groups. So, these NH groups can interact with this Cl minus to go for the hydrogen bonding interactions, and we get the corresponding complex species where this hydrogen bonded form of Cl minus is there. So, it can also be considered at the corresponding complex of Cl minus. So, in this all these cases there are some equilibrium, how strongly they are bound to the corresponding host or this other anion binding site, because anions are also loosely bound in all biomolecular reactions, also in protein molecules, in DNA, RNA and all other cases. In the biological system also this type of anion binding sites are very important, and there we call them as the corresponding receptor sites for binding the corresponding anions, because in true sense the Cl minus binding to some site where metal ion is not involved, we cannot consider them as the corresponding formation of the metal complexes. So, in all these cases we can have the corresponding constant for these formation. So, we can measure the corresponding K values for these complex species. So, host guest complexes and complex anions are therefore very much important in this particular study, and the stability constant or constants what we can get from the informations will be required to calculate the corresponding concentrations of the complexes in solution. That means, if we know the corresponding concentrations of the reagents, then we can find out the corresponding concentration of the complex species. That means, at equilibrium we have the specific concentrations of the metal ion, the ligand and the complex species. So, depending on the progress of the reaction towards the complex side, we can find out the percentage conversion of the metal ions to the desired metal complex, and we can find out the corresponding equilibrium constant or the formation constant value for the binding of the metal ion to the ligand. So, in that particular case, the formation of a complex with ligand can be considered as a typical acid base equilibrium, and there is a competition for the ligand L between the metal ion Mn plus and the hydrogen ion. Because we know that there are some sites, this is the cationic species, the metal ion is the cation and the hydrogen ion is also the cationic species. So, if the ligand is a lone pair donor or a base or typical anionic species, then the ligand can have some corresponding affinity to bind the metal ion, as well as it can have the corresponding affinity for the H plus ion. So, we have these two processes, these two equilibrium processes are simultaneously operative between H plus L and between M plus L, and for simplicity we have not added charge on the H and the charge on the M. So, the competition between the formation of HL and ML is important, and if the ligand is an anionic one, so it basically gets back the corresponding proton to get the corresponding neutral ligand. So, if we have some site, it is also true for any amino acid or some biochemical reactions, that phenol part is available, and this phenol part we can consider as that is a part of the corresponding amino acid, and this particular one basically after deprotonation gives us the corresponding anion. So, after removal of H plus, it gives us the corresponding anion, then it binds the corresponding metal ion center in this form. So, this particular species which is there at the central part, that means the corresponding phenoxide ion, this will have the typical tendency, that means the competitive tendency to bind the Mn plus or L plus. So, for deprotonation we use some organic base, say NET3, and NET3 can take up the proton forming the corresponding NET3H plus triethyl ammonium ion. So, this triethyl ammonium ion will be there and this will be free. So, there will be no competition for this phenoxide ion to bind with the proton which were originally bound to the system, because it has already been taken away by the triethylamine molecule. So, in that particular case only the added metal ion Mn plus can bind to the ligand system and is forming one MO bond from the phenol unit. In that particular case only we cannot have the corresponding competition for the L species for both H and M. But otherwise when we just simply add the ligand with that of the metal ion, that means if we just use the corresponding phenol unit with Mn plus without considering and without thinking of the first step, that means the removal of the H plus, then we will find that this O minus can have some binding tendency to H plus or to Mn plus. So, there will be two competitive pathways for binding the phenoxide ion to the Mn plus and the protein, and therefore, we see that this H plus L and M plus L situation is there all the time. And for the second case, if we can consider that Ml is forming out of M and L, and if we can measure the corresponding concentrations of the fragment like Ml as well as the starting concentration L and M, then at equilibrium what are the corresponding concentrations, if we can measure, then we can write down the corresponding equilibrium constant, which is nothing but the concentration of the complex formed, the Ml, the concentration of the Ml, the concentration of the M left over at the equilibrium, and the concentration of the ligand at that particular point as equilibrium concentration of the ligand will give us a corresponding constant value as beta. So, in that particular case we will find that both stepwise and cumulative constants are functioning when we can add more than one L to the metal ion. That means, we can go from M plus L to M plus 2L. So, M plus 2L can give rise to Ml2, and where we get the beta 1 step and the beta 1 2 step, that means both the steps are operating, and we have the corresponding cumulative constant which is beta 1 2 is the concentration of the final species which has been formed from Ml, because this can also be written in the form of the Ml plus L. So, Ml plus L also give rise to Ml2, but when we are directly getting all these species like M plus n number of L values, n is the coordination number, if it is 12 it can be 12L. So, we just see there that beta 1 2 will be the final concentration of the final species what we are looking for the corresponding compound, and the metal ion remaining in the medium, and the concentration of the L what is there at the equilibrium powered by the number of species what we are using. So, the stepwise constant, that means in first step, that means addition of 1 L, which is also true this, because this particular complex formation all we know is related to the corresponding binding of ammonia molecules to the silver ion. So, how the corresponding reaction what is taking place for silver 1 reacting with ammonia giving rise to, in the first step, the silver amine complex or 1 amine is present. Then in the second step, it is reacting with the second ammonia molecule, giving rise to AgNH3 whole 2 plus molecule. So, we should know about the corresponding concentration, what is forming over there, and the concentration what is remaining over during the equilibrium process as the corresponding silver ion concentration as well as the ammonia concentration. So, in these two steps we have K1 and K2 and we call them as the formation of the complexes in one step at a time. That means, if both K1 and K2 is operating together, we get only beta 1 2 in a single step. So, when the first ligand, the first ammonia molecule is coming and bound to the silver ion, we get the K1 value, and when the second is coming to the first one, that means silver amine single species, one NH3 bound silver species plus another NH3, giving rise to the silver diamine complex, giving rise to the corresponding K2 as Ml2 by Ml and L, product of L. So, we get how this beta 1 2, so the beta 1 2 is we are getting the product of these two. So, product of K1 and product of K2 is basically the beta 1 2. So, that gives us some idea that the beta 1 2 will be the K1 and K2, the product of the stepwise formation constants is the corresponding cumulative constant for the complex formation. So, this particular expressions, if we can have n number of species, if the n value is equal to 4 or 6, we can have K1, K2, K3, K4, K5 and K6 like these. So, these type of expressions are also useful for any such reactions like that of when we get say species like that of the metal ligand species itself. So, if we have already the metal ligand species and if we can talk about further binding of any other ligand species, that means the L prime or similar thing, and when we find that these sort of things are also possible in some protein envelope, one such good example we will talking in one of our future class also, that is the binding of hemoglobin during the corresponding oxygenation reaction. So, O2 binding by the hemoglobin molecule. So, L prime would be our oxygen molecule and we have the metal center as iron. So, this metal center is our iron center and this L prime is our O2. So, the binding of the hemoglobin molecule of O2 can also be studied in the same fashion by the different steps if there are more than one steps. So, in the biological system also we can monitor the oxygenation reaction using the same procedure. That means, the beta 1 2, beta 1 2 3 or beta 1 2 3 4 can also be monitored for a reversible reaction like the oxygen binding to the iron center in hemoglobin or in some cases also with myoglobin molecule. So, we have the beta values for different types of complex formation. So, once the complex is formed, so it can be the typical metal ligand assembly or it can be the bound oxygen to the hemoglobin or the myoglobin molecule. It does not change much, but some of the ligand can come off or be exchanged for other ligands. So, we see that there is a ligand exchange reaction because typically when we go for some reactions like that of the corresponding water bound metal ion with some replacement with say ammonia molecule, we find that water ligands, that means the aqua ligands, are substituted by the amine ligands. And this particular transition from the aqua complex to the amine complex, there will be some control by the thermodynamic factors that relate directly to the Ka values, the formation constant values. So, we see that the water molecules, the 6 water molecules are bound to the nickel and is a ligand substitution reaction in a stepwise manner again. That means one after another amine molecules are coming and substituting the 6 water molecules already present to the nickel 2 ion, giving rise to the corresponding binding of 6 ammonia molecules to the nickel center and with the corresponding removal of 6 water molecules. Or we can consider that in another way, that we take some other ligand with that of the formed species. That means, when we have the hexaamine nickel 2 ion is formed from the hexaaco nickel 2 ion, then it is further reacting with 3 molecules of ethylene diamine, and ethylene diamine is also nicely substituting all the 6 amine molecules. That means, all the 6 NH3 molecules are being replaced by these bidentate ethylene diamine molecules, such that the binding potential, the binding strength of these bidentate chelating ligands ethylene diamines are more compared to the binding of the ammonia molecules to the nickel center. As a result, we get tris ethylene diamine nickel 2 ion with the removal of 6 ammonia molecules. So, 6 ammonia molecules will be removed from the system and we will be ending up with the corresponding tris chelate of the nickel molecule. So, one Lewis base is replaced by the other. So, we have the first step, the monodentate ammonia molecules are there. Monodentate ammonia ligands, they are also Lewis bases, they are bound to the nickel center. In the second step, we are considering as the ligand substitution reaction by another chelating base, which is removing the bound ammonium groups around the nickel ion. So, we want to know the corresponding K value, that means the formation constant value, how this K value is favoring us from left to right towards the formation of the corresponding tris chelate for the compound. A large K value would mean that coordination by En is favored over ammonia. So, if we are able to measure that experimentally these values can be measured, if we are able to measure the corresponding Ka value in solution for the reaction of ethylene diamine with NH3, we can consider that the binding of ethylene diamine, that means the coordination of ethylene diamine is favored over NH3. That is why ammonia molecules are leaving behind and those positions are taken up by the ethylene diamine molecule. So, we find that the binding of 3 ethylene diamine to this system. So, how we write the corresponding formation constant value is that the formation constant value is the species which are present on the right hand side by the species which are there in the left hand side. That means, all the species, the formation of this hexamine compound which was been taken place in the first step, as well as the formation of the new chelate complex, as well as the corresponding concentration of the 2 different ligands. So, this also gives us some opportunity to find out the corresponding K value during the replacement of one ligand by another. So, this is the situation where we see that the 6 ammonia molecules are attaching to the nickel center and ethylene diamine is coming. So, in the first step what is happening? 2 adjacent ammonia molecules are being replaced by one ethylene diamine. So, these will have some attached H2 molecule groups also. So, these are NH2, CH2, CH2, NH2. So, this is the ethylene diamine unit which will replace 2 ammonia molecules. So, this equation we were constructed with the 3 En molecules replacing 6 amino molecules, they must occur in a stepwise fashion. Therefore, we considered that in the first step, one ethylene diamine molecule is attaching to the molecule, but it is very difficult to isolate in the solid state and characterize by some structural methods or by some spectroscopic methods to identify the species where the nickel center is bound to 4 ammonia molecules and 1 ethylene diamine, because this is some kind of some intermediate species which is forming within the solution, and the stability of this particular intermediate is not so high such that we can isolate this particular intermediate by using some other anion. So, first step is definitely we can write in this form that 4 ammonia molecules and 1 ethylene diamine, removing 2 ammonia molecules from there. So, the formation constant for the first step would be the concentration of this species, then 2 ammonia molecule, the concentration of these, what is coming out there, the concentration term for the ammonia, and the hexamine complex and the ethylene diamine. So, this would be the K1, because we are breaking the entire reaction what is forming in a single step for the K value for the triskeleton formation. So, in the second step we utilize the second ethylene diamine molecule. So, second ethylene diamine molecule will come and bound by replacing 2 more ammonia groups from these 2 sites. They are cis positions and they are adjacent to the first chelat ring. So, the second chelat ring is also attaching to the molecule, and we can write this particular equilibrium. So, how we can break the entire reaction basically by utilizing the reaction for NiEn NH3 whole for 2 plus En, giving rise to NiEn2 NH3 whole to 2 plus 2 NH3 molecules which were present. So, in this particular case also we should be able to write the formation constant by knowing the corresponding concentration of this particular species which is forming as the intermediate species. So, at the intermediate species, if we are able to know the corresponding concentration of the intermediates, the very transient species which are very fastly disappearing from the solution medium, because it is immediately reacting with the third ethylene diamine molecule. So, if we are able to determine the corresponding concentration of this particular species which is transiently forming in the reaction medium, we should then be able to find out the corresponding value for the second step, that means the K2 value for the reaction. Now, we see that the entire Kf value, that means the Kf value will therefore be the product of the corresponding Kn value for the formation of the species by the attachment of 1 ethylene diamine molecule, then the formation of the second species, that means the K2 value with 2 ethylene diamine group attaching to the nickel center, and then third the K3 value for the formation of the triskeleton, and the other individual, that means the species, that means the concentration of the species what we are utilizing to write down those expressions on the right hand sides. So, there are some common things. So, this will cut with these 2 values will cut, and these are basically NH3 power 2, NH3 power 2 and NH3 power 2 will give rise to NH3 power 6. So, we get basically the Kf value, the overall formation constant, the cumulative constant for the formation of the tris ethylene diamine nickel 2 will therefore be this one, NiEn3 concentration, then NH3 power 6 and NiNH3 6 concentration and En concentration powered by 3. So, we can find out the K for the single step reaction where tris ethylene diamine nickel complex is forming from the hexaamine nickel 2 species. So, the total formation constant is therefore what we can conclude from this particular part, that the total formation constant, the Kf is nothing but the product of the formation constant for each step. So, if we have 3 steps like K1, K2 and K3, we get the Kf value as the product of K1 into K2 into K3. So, we have the Kf, K1 product K2 product K3 and so on. So, in this particular case also, where we know that hemoglobin molecule is nothing but is a tetrameric species, is a tetramer. So, tetramer means immediately we can see that we can have 4 iron sides. So, is a heme protein type of thing. So, 4, it has some quaternary structure. So, the quaternary protein structure of hemoglobin tells us that it has 4 iron center, and all those 4 iron centers can be utilized for binding of iron. So, this oxygenation reaction of the tetrameric hemoglobin molecule can be considered as a corresponding binding of the O2 in a stepwise manner. So, we have the corresponding K1 value for the binding of first O2 molecule to the first iron center, then the second O2 molecule to the second center, which will be K2, then the third one is to the third center, which is K3, and the fourth one, which will be the corresponding K4. So, how these values are interrelated, that will be seen if we just know the corresponding protein envelope of the entire tetrameric structure. So, there will be a cooperativity, that means the cooperation is taking place when first center is getting oxygenated, that means when K1 is there. So, when first center is oxygenated, so there will be certain movement in the protein structure which allows the corresponding binding of the second O2 molecule feasible, that means the dependence of the K2 value on K1 is seen from this kind of cooperative binding of O2 molecule to the hemoglobin centers. So, all together we have the K1, K2, K3 and K4, and is a very complex process for the oxygenation reaction, but the cooperativity of the hemoglobin molecule for oxygen binding, which we can consider as when we have hemoglobin which is in the deoxy form to that of our hemoglobin by binding of 4 O2 molecule at 4 different steps. So, 4 different steps will be required to get the fully oxygenated hemoglobin molecule from the deoxyhemoglobin, and the steps required for the oxygenation reactions are dependent to each other, which will also be known to us the way the reaction goes for the corresponding reversible way for the deoxygenation, because this can go and this can deliver these oxygens to these myoglobin molecules. So, myoglobin molecules are then the acceptors, and these oxyhemoglobin molecules can go for deoxygenation reaction. So, these are all interrelated, but for the time being we will come back again on this aspect of binding of the biological system, where we see again that these K1, K2, K3 and K4 values are clearly observable in case of hemoglobin molecule for binding of O2. So, the overall formation constants for NiEN3 2 plus from NiNH3 whole 6 2 plus can be directly written like this K value once we write the direct reaction of NiNH3 whole 6 2 plus with ammonia in presence of ammonia and the formation of the corresponding NiEN whole 3 molecule. So, what are the thermodynamic role for the formation of these species, that we will see from some thermodynamic comparison for the formation of these different steps. So, a value which is related to the coordination equilibrium, that means the equilibrium is there due to the coordination, and a large K value would mean that coordination by ethylene diamine is favored over NH3. So, if we are able to monitor the corresponding K value due to the binding of ethylene diamine on the amine complex of nickel, we can simply assume that the binding is favored for the chelate ring. So, the reaction what we can see for the other one, that means where we see that the ACO complex is binding directly with ethylene diamine. So, that is also possible. So, directly from the ACO species we get the formation of the trischelate of the bivalent nickel, and we find out the corresponding values for the formation of these, and for the reaction which is directly forming from the ACO complex we can find out the corresponding K value as 1.1 into 10 to the power 18. Just we simply compare the magnitude of these values. So, the numerical values of these constants can give some idea that how the reaction is favored from left to right, how the K values are higher if we are just simply talking about the corresponding monodentate substitution reactions of ammonia ligands which are replacing the water molecules, or in other case the ethylene diamine molecules are replacing the water molecules. So, straightway when we are getting the corresponding trischelate from the ACO complex, we have a corresponding K value of the order of 10 to the power 18. So, we see that when we have the corresponding K value from the amine complex, we get the corresponding value for these where the 6 amine groups are there which are substituting with ethylene diamine giving the trischelate, and this trischelate is responsible for the removal of 6 NH3 groups. So, in these two steps, that means this was the first one, that means if we just get the values for the formation of these, that means the formation of the corresponding values for this K2 and the formation of the corresponding K value for the K1 for the amine complex and the ethylene diamine complex, both of them are forming from the ACO complex. We get some ratio like this, which is 1.1 into 10 to the power 18 divided by 5.3 into 10 to the power 18, and this value is definitely nothing but the formation of the trischelate from the amine complex. So, that way we get the corresponding formation constant value for the direct formation of the tris-ethylene diamine complex from the hexaamine complex, and in that particular case we find the corresponding value as 2.1 into 10 to the power 9. So, in case of the corresponding formation of these values for these corresponding tris-ethylene diamine starting from the water molecule, that means the aqua complex, or from the amine complex. So, these values basically gives us some idea that how we get the corresponding values for the thermodynamic stabilities of these complexes. So, it gives us some information that the thermodynamics of the metal ion complex formation provides some significant informations about the stabilities of these complexes, and in particular it is useful in distinguishing between the two parts. So, the thermodynamic stability constants can have two parts. One is the corresponding enthalpic term and another is the corresponding entropic effects. So, the enthalpic effects, what is the heating effect, how the corresponding enthalpy values are responsible to detect the corresponding formation of the complexes, and these enthalpic values depend on the bond strength, and entropic effects have to do with the changes in the order and disorder of the solution as a whole. So, how strong bonds we are able to form such that when the ethylene diamine is reacting with the nickel center, so we have all these positions, whether it is bound to the water molecule or ammonia molecule. So, we have the corresponding values for delta H also and the corresponding values for delta S. So, we have the contribution from the enthalpy as well as the entropy, but in this particular case we are replacing the water molecule by the ammonia molecule, but the nature of these bonds from NiO to NiN we are changing, and this nitrogen bond is coming from the ammonia molecule. And in the second step, when we are utilizing the ethylene diamine, is forming the chelate ring, and in that particular case the NiN bond of different type which is coming from the ethylene diamine is forming. So, we can have the relative contribution of the bond strength and the order disorder phenomenon related to the more ordered form of these two groups. In this particular case, when one ethylene diamine is binding towards the nickel 2 plus ion, it is removing 2 NH3 molecules. So, more number of molecules are removing from the system. So, we should have some contribution from the entropy term. So, this entropic effect will have some changes on the order and disorder of the solution as a whole. So, how the entropy effect can contribute for the solution thermodynamics for the binding of the chelate ring to the metal ion. So, for that equilibrium constant which is related to the standard Gibbs free energy. So, both delta H and delta S, they are related to the delta G standard particularly. So, when the standard G values, the delta G values are there which should be related to the corresponding enthalpy term and the entropy term by the corresponding equilibrium constant value which is the beta value. So, delta G0 will be equal to minus 2.303 RT log to the base 10 beta. So, this is the constant value what we are looking here for the determination of the stability constant and the formation constant, and this determination of beta value can also give us some idea about the corresponding delta G0 value for the reaction system, where we know the corresponding temperature, and the temperature effect can also be monitored because we know if the corresponding beta value is known, we can find out the corresponding delta G0 values for these reactions, such that the free energy is made up of an enthalpy term and an entropy term, that we all know that it has two parts. So, how this delta G0 is taking up their individual contributions from the entropy term and the enthalpy term, that we will just see if we just can monitor or equate these delta G0 values with the delta H0 value or the T minus T delta S0 values for the different standard conditions. These are for the different standard conditions. So, once we measure these values for the free energy change, we can correlate them for the corresponding enthalpy term and the corresponding entropy term for the binding of say ammonia molecule around nickel, as well as the binding of the corresponding ethylene diamine molecule to the system. So, these values basically can give us some idea for the corresponding silver amine complex, where we get the corresponding K1 value for the silver amine complex, as well as for the corresponding values for the second step. So, we get the both K1 and K2 values for these cases and the different values for the equilibrium as well as the enthalpic contribution and the entropic contribution. So, for the formation of the corresponding silver amine complex with a coordination number of 2, we will find these two contributions, that the enthalpy contributions are favored. That means both these two cases, though the steric crowding is not much, so they are favored both for this enthalpy contribution, and the entropy contribution is mostly favored in the second step, not in the first step, due to the formation of a corresponding silver amine complex with a coordination number of 2. And in this particular case, which we are not talking about the corresponding chelate formation, we do not have some opportunity, we do not have the corresponding opportunity to see how these delta S values can contribute only for the chelate formation. Thank you very much.